In this video, we're going to discuss absolute mins and maxes. So in the last video, we talked about local mins and maxes. And in this graph here, I have a couple of those. That would just be where the slope is 0. We call that a local max or local min, and there can be multiple local maxes or local mins. Notice I'm taking this back to 2 dimensions in Calc 1 just to clarify things, and then we'll up it a dimension. So a local max and min is where the derivatives are equal to 0. The absolute max and min, there's only going to be one of them. There's only one max, and that is the max over the entire interval. So if you look from x equals a to x equals b, you search the whole thing for the highest value. The local min, the absolute min, you search the entire thing for the minimum value. In this graph that I have, it happens that the local min is also the absolute min when we look from A to B. But notice that the local max was not the absolute max because the graph kind of goes up at the end. The absolute max ends up being a little bit different. All right, so in this process of finding absolute maxes and mins, we would have to find critical points to check and see if they are the biggest or the smallest. And then we also need to look on each side of the graph. We would have to check at x equals a and at x equals b to figure out whether that is the biggest or the smallest. All right, so let me give you kind of a list of steps so that you can find absolute maxes and mins. So the first thing that you want to do is find the critical points. So find the critical points. And remember, you do this by setting the partial with respect to x equal to 0, the partial with respect to y equaling 0, and then you get these x, y values that are the critical points. So you want to find the critical points. And you also want to find I'll just put the value of the function, so the value of f at those points. So we're looking for how big f is. So in all of this, we're looking for how big that function is. Is it the biggest that function gets or the smallest? So this checks for local maxes and mins and what their values are. And then the next thing that you need to do is to search along the boundary. So search the boundary and you find values of x. Find values of the function all along the boundary, and then see what value of f is the biggest. That would be your absolute max, and what f is the smallest. And that would be your absolute min. All right, now this whole searching boundary thing, in 2 dimensions, that's pretty easy because your boundary are single values. They're just an x equals a number and an x equals a number. But when you go to 3 dimensions, our boundary is going to be a 2-dimensional shape. So the boundary is a 2D shape that we have to trace the whole thing to find the biggest and the smallest. All right, let's do an example. Okay, so let's find the absolute mins and maxes of this function. The function is 3 plus xy minus x minus 2y. All right, so the first thing we needed to do is find those critical points. So I'm going to take the partial of f with respect to x and the partial of f with respect to y. Now the partial of f with respect to x, I'm keeping everything constant except x. So that would be y, and then the derivative of negative x is negative 1. Then the partial of f with respect to y would be, x minus 2. So to find the critical points, we're going to take each one of those and set them equal to 0. From the first one, we get y equals 1, and from the second one, we get x equals 2. So we have one critical point. So our critical point is the point 2, 1. So now to find, let's find the value of the function at that critical point. So I'm going to take 2, 1, plug it back up into this original equation. So I get 3 plus 2 times 1 is 2, minus the x value, which is 2, minus 2 times y, which is 2. So 3 minus 2, so the function at 2, 1 is equal to 1. Okay, so there is the critical point and the value of the function at that critical point. So now I'm going to kind of separate this out because now we need to look at the boundary. And the first thing I'm going to do is graph it. Oh, I need to give you a boundary. So I'm sorry. Let me include in here the boundary, and I will just graph it for you. So the boundary is, here's my x, my y. It is going to be a triangle that is 5 long there, 1 long there, so it's 4 long along the base, and 4 high. Okay, and I think that's all we need. Okay, so our boundary is this triangle here with 1 leg there. I'm going to do these all in different colors. 1 leg there, and let's choose purple and do the hypotenuse in purple. All right, because as we search the boundary, we're going to have to search each different one of these lines separately. All right, so let's do the green one first. So line 1. So the first thing that I do is define it. Now that line is the line y equals 0, where x goes from 0 to 5. So now if I take y equals 0 and plug it back into this function, I'm looking for the values of this function that are the biggest and the smallest. So if I plug in 0 back into that function, the function at any x and at y equals 0 is going to be 3, that next term is going to go away, minus x, and then 2y just stays there. All right, so now I take into consideration that x can be anywhere between 1 and 5. Because this is a linear function, I know that 1 and 5 are going to be the mins and maxes of this function. If that was an x squared, you need to be careful because you need to take another derivative and to find a critical point just for that line. I'll show you an example of this. The second line will give that to us. Oh no, I'm sorry, it's the hypotenuse that gives that to us. Anyways, so if I plug in 1 into this function, so the function at 1, 0, we're going to get 3, and the function at 5, 0, we get negative 2. Now, if you look right now, we have 3 different values of our function, and if we're looking for the biggest and the smallest, right now just notice that this value of the function is the biggest and this value of the function is the smallest. The critical point does not, although it is either a local min or a local max. I guess it could be a saddle point as well, but it does not create a absolute min or max. All right, so there's that green line. Now let's go to line 2. Okay, so the turquoise line here, so I'm going to call that line 2. So let's define it first. So that's a line where x is equal to 1 and y is in between 0 and 4. And now I'm going to take that x, plug it into the function. So the value of the function at 1 and at any value of y is going to be 3 plus I'm going to keep that 3 in mind because I know I'm going to subtract a 1 from it in just a minute. So actually maybe let's just do that. So we get 3 minus 1 is a 2. And then we've got a plus y. And then a minus 2y. So it looks like we're at the end of all of this going to get 2 minus y. Let me plug in 1. Now, once again, this is linear, so now I can check just at the bounds of y. I don't need to check in the middle of it. So I'm going to find the value of the function at, x is 1 for all of these, at 0, and the value of the function at 1 for all of these, and at y equals 4. If I plug in 0 for y, I get 2. If I plug in 4 for y, I get negative 2. All right, so I've got all these different values here. We'll look at those in just a minute, but let's look at that third line first. So line 3. So line 3 is the line where, since it's a value of 5, that way if I continued this line, the slope goes up 4 over 4. It's a slope of 1, so it is it's a slope of negative 1. And then the y-intercept is going to be 5. Where it will cross right here would be 5. Okay, so that's that line. And then x will be in between 1 and 5. If I look at the x values for that line, it's in between 1 and 5. So just like the other ones, I'm going to take that y function and I'm going to plug it into this function up here. So we get that the function at, let's see, x is going to stay as x is, but every time we see a y, we're going to plug in negative x plus 5. So we're going to get 3 plus x stays as x, but y is going to be negative x plus 5. X stays as x there, minus 2 times y, which is negative x, sorry, I'm running out of room, plus 5. So let's simplify this. So if I look at all of the numbers, I have a 3, and all those are going to have x's in them, and then it looks like I have a minus 7. Oh, I'm sorry, that's a 2 times 5. I think I just did that fast in my head. So 2 times 5, that's a negative 10 plus 3. There we go, there's a negative 7. Let's look at the x's. I've got a 5x. Minus x would be a 4x, and then I've got plus 2x right there on the end of that, or towards the side of my paper here. And so all together, I think I've got 6 x's. And then if I look at the x squared, so I've got a minus x squared. All right, so notice the difference here. These guys only had x's. This now has an x squared, which means that even within 1 and 5, there could be a max or min within that. And so what we need to do is do a little mini max or min problem within this problem. We are going to take the derivative of this function we just found. So if we take the derivative of this, we get 6 minus 2x. We're going to set that equal to 0, and we get x equals 3. Now we need to check to make sure we care. Is x equal 3 in these values? Yes. So we care about it. So we want to check it as well as 1 and 5. If it wasn't in those values, we don't need to check it. So we need to find, and by check I mean find the value of the function. So we need to find the value of the function at x equals 1. And when x is 1, here's my y value, which is negative 1 plus 5, so that's a 4. Then I need to check the value of the function when x is 3. 5 minus 3 would be 2 for the y value. And the value of the function at 5 minus 5 would be 0. Okay, so these functions, these are a little bit more complicated numbers and there's a little bit of an easier way, I can actually plug these into this function. So all I need to worry about are the x's. So I've got 6 minus 7 when x is 1, so that's a -1. Minus 1, it looks like I get a -2 at that 1, 4 point. Now if I plug in 3 times 6, so that's 18, and a -9. So 18, and then minus 9, I get -2 there as well. And then if I'm sorry, I think that's a +2. That is a +2. Then if I plug in 5, 0, so if I plug in 5 for x, so 30 minus 25 would be 5, -7 plus 5, so that's a -2. Okay, so all of these values of this function. So now I need to search through all of them. So I'm looking at this guy, this guy, this guy, that guy, that guy, that guy, that guy, and that guy. I'm looking through all of those for the smallest and the biggest. So as we look through all of these, it looks like we got a value of 3. When x was 1, we got, yeah, something's not right here, right? I'm so sorry. I think it's the end of the day here, and I just said that 3 minus 1 was 3. That was a good one. Okay, so let's try that. 3 minus 1 is 2. All right, hopefully that's the only mistake I made in here. We'll see if I can find any others. All right, so as I search through this, it looks like 2 is the biggest value and 1 is the smallest. Okay, so the max value is 2. So the max is 2, and that max occurs at, it looks like a couple different points. Well, I've got 1, 0 up there twice, so it occurs at 1, 0, and it looks like it also occurs at 3, 2. And I think that's it for where it's 2. For the min, if you look through all of these, the min is -2. And that min occurs at, let's see, the 0.50, 0.14, and then it looks like we have 50 again and 14 again. Okay, so here's my absolute min and max value. If we graphed this, our z value would be 2, and that would occur at 2 different points. The max z value would occur at 2 different points, and the same with the min, but the min would be at -2. And there's one more thing I need to mention, and that's right in here. If you get a critical point that is not within the region, ignore it. We only care about the region. So if you get a critical point that's in that region, ignore it. Okay, I think that's it.